We're talking about adding vectors. We can add vectors together graphically like we've been doing, and we can also break vectors apart into their x and y components. So in the first part of this worksheet, that's what we're doing. We're breaking these vectors that were given into their x and y components. So each of these has some magnitude in its x component and some magnitude in its y component. So we use our parallelogram rule that we know to find where the x and y vector components would be. And we just draw them in like that. In this case, the y component is positive and the x component is negative. Here for vector b, both the x and the y components are negative. So I draw my parallel lines here to find my x and y components. For vector c, we just are given this vector on the x-axis, so it actually doesn't have a y component. And so cy would equal 0, and cx is just equal to c. And you could say that it's going west. For this second part, we have to find the vector components and then determine their numerical values. So we're looking for magnitude and direction. So graphically, we find the vector components like we were with our parallelogram rule. There's our y component and there's our x component. And you should be able to see that we're creating two right triangles here. And so with the right triangles, we can use what we know about sides and angles to find missing sides and missing angles. Here we're given a 130-degree angle, making this one 50. So our 90-degree angle minus 130. And then this angle here is 40 degrees. So we can use this 40-degree angle. We can use either angle really to find the rest of our missing pieces here. So to find our y component of A, we use trigonometry and we use the cosine of our 40-degree angle in this case to find the y component of A. And that would be 3.8. And for the x component of A, we use our sine of angle theta to find the x component of A, which is negative in this case, 3.2, because we have a negative x component. Okay, and again, we're just given an angle and we're given a magnitude of a vector. So we can find the magnitudes of these x and y components and any missing angles if we want to. So again, we use our 30-degree angle here to find the opposite side of that angle here, or our y component. We use the sine of theta. And to find the adjacent angle, the adjacent line, or the x component, we use the cosine of our angle to find the x. So we have our hypotenuse, the magnitude of our hypotenuse, b, which is 4, times the sine of the angle 30. And we get negative 3.5 and negative 2.0 for y. In number 18, we have an x and y component. And we have a 45-degree angle here, breaking this 90-degree angle in half, which means that both of these components are going to be equal, whatever they may be. We have our hypotenuse here, or our vector, at 5, and then we can use our cosine of our angle to find either one of these vectors are going to be equal. And we get positive 3.5 for x and negative 3.5 for y. And then this last one asks, what's the sum of the vector d, which would be the vector a plus b plus c. So what you do here is you add all of the x components of d, which would be all of these x components, add those all together, and then you should get negative 3.2. And then you add all of the y components together. And make sure, this is why you need to pay attention to your signs, because you have 3.8 minus 2.0 minus 3.5, and you get negative 1.7. And now those last couple questions are conceptual questions asking us if a vector can have a component equal to 0 and still have a non-zero magnitude. So if we look here at number 15, you should know that the answer is yes. We have a vector that has a component equal to 0. Its y component is 0, and it still has magnitude. The next one, can a vector have 0 magnitude if one of its components is non-zero? So if either one of these components has magnitude, then your vector is going to have magnitude. So that would be no. This second half of the sheet, we're given the x and y components and asked to build the vector. So we're adding the x and y components together to make the vector. So here you just draw your x component, 3, your y component, -2, and you find graphically your resultant vector. That gives you an idea of what you're looking for. And then you can choose either one of these angles to work from. We'll use this angle here. And you find your missing sides using what you know here. You have 2 sides and you're missing your third. So we have -2 squared plus 3 squared equals c squared, our missing side, and we find that that is 3.6. We've found the magnitude of our vector. And now we want to find this angle here. So we have 2 sides and we want to find the angle. We can use the inverse tangent of our 2 sides to find theta. We should get 30 degrees, and that would be this angle here. So you would say 30 degrees south of east. We're using our small angles again. This second one gives a x of -2, y of 2, and our resultant vector somewhere in here. There we go. And so again, we use the Pythagorean theorem to find our missing side. Or in this case, it's a b, isn't it? We get b equals 2.8. And we can use our in this case we're given two sides, and we can use our inverse sine of the opposite over the hypotenuse to find our angle. And it should come out to be 45.6 or so. This next one, we have no x component, we only have a y component. It's -2. So c equals -2, and the angle is just south, or you could say 180 degrees. Okay, so again, we're given a vector and its magnitude, and we're given an angle, and we need to find the magnitude of its x and y components. So this vector, just like in 16 through 18, will have a y component and an x component. And we use our Pythagorean theorem to find these x and y components. The only difference here is that we have to pay closer attention to our angles because they mess with the axis on 26 and 27. So we use the Pythagorean theorem to find our missing sides, and then we can use our trig. Oops, I'm sorry. Y over 5, and then the cosine of our angle will be our x over our hypotenuse. Okay, so these are just really just like 16 through 18, except for we have to pay closer attention to our angles. We have a big 60-degree angle here, which makes this one the rest of that 90-degree angle. And then you just use those angles to find your x and y components. And then here we have this big angle here, which is the rest of this 180-degree angle, so it's 75 degrees. And leaving us with this smaller 15-degree angle here. And so we use these angles and this vector to find our components. Okay. This motion on a ramp part just asks you to draw arrows showing the vectors of the motion of this ball. And so the vector that we want to show here is the acceleration, which depends on gravity. So this ball is rolling downhill and it's accelerating that way. Down here at the bottom, there is no acceleration. And then as the ball rolls up this hill, acceleration is still pointing downward against its motion. And then as the ball comes to a stop up here, the acceleration is 0.